There are many places in cognitive electronic warfare where we should like to employ machine learning approaches, particularly neural methods. But the problem that occurs is one of a responsibility for explainability and reproducibility. To explain that responsibility, it may be best to just look at the kinds of AI that exist, and we can see that symbolic AI on the left-hand side and machine learning on the right-hand side and evolutionary algorithms in the middle. And symbolic AI has the ability to be explained by the human as its abstraction is closer to the human, and machine learning has a further abstraction from the human and has an explainability problem. However, machine learning, obviously machine learns, and symbolic AI has a problem with machine learning. In the sense of the evolutionary algorithms are a bit of a different case here, but the solution that is provided may well not be the most optimal one. It is one that just survives the fitness landscape. What we really want is a symbolic AI's explainability with a machine learning's ability to learn. And that brings us to an area of interest called neurosymbolic AI. And the area of responsibility, therefore, that we're talking about is the explainability question for machine learning, artificial networks, convolutional networks, and deep learning. So what we have in that area is two major issues. One is explainability, how do we conclude exactly what has been learned, and reproducibility, which is making training a system consistently time and time again, without questions of what's most optimal and what's most safe. And the first approaches to this proved that we could replace the random forms in the initial state with a non-random sequence of numbers and could get an equivalent result. And the second attempt at this improved that by using Xavier and HE element and got an equivalent result. And we can see here in these two diagrams below, the random on the right, on the left, and the non-random on the right. We can also see that there's an additional advantage in clustering in the activations, which is an advantage for explanation using rule extraction techniques. As the activations are adjacent, they are almost nearly generalized. So that sort of provided a question for, an answer for perceptron layers and dense layers, but part of the area of which we are most interested and has brought most of the benefits in recent times has been convolutional networks, and a different approach was required. And the inspiration for this was the Hubel and Wiesel work with cats and spider monkeys under light anesthetic while stimulating the retina with spots and images. And what we provided was a number sequence that was more stripy and less spotty, like the random forms, and that had an advantage of being more predisposed to the application area. So it invoked earlier learning, improved the overall accuracy, and had the reproducibility, repeatable determinism benefits. That, when applied to more complex problems, in more complex data sets, like this one of aircraft on runways, we could see the benefit of 68% accuracy instead of 29% on the first learning session. So many parts of that were published along the way, and we continue with that research and towards the explainability questions, which are on the foundation of repeatability and reproducibility.